Hello everyone, and welcome to your final Thomas Tool Tuesday. Today I'm going to be going over the Unified Forecast System as my grand finale here at the university. This is going to be what replaces the current modeling system in the United States. So why are we unifying? The main reason is to reduce complexity. Currently, we have a large variety of different dynamical cores, we have a large variety of different model resolutions, and all of that takes up a lot of computing power, a lot of resources, and makes it difficult to continue to develop on what's performing the best. So we are going to a streamlined framework within the United States here in short order. As of right now, that's expected by August. Could get delayed some more, but I'm expecting it by the end of 2026 at the very latest. So let's talk about the current complexity. What do we have? Well, the current global model is the GFS. This is version 16. That'll be important later, but GFS version 16 is what we currently have. And there are a variety of offshoots from that produce different model outputs. The first is the SREF. The SREF is a combination of two different dynamical cores. That's the ARW and the NNMB, and this will matter in a second. But the main thing about it is that it is an ensemble that uses GFS initial conditions with slight changes and a variety of different weather model dynamical cores and physics schemes to give you an idea of what the future looks like. This is a lower resolution model, a lot like the NAM or the RAP. The first of these models that offshoot is the NAM. This is a pretty much control member of the SREF. And the NAM goes out to 84 hours. So we see the NAM, that's pretty good. And then we have the NAM 3 kilometer. That's the high resolution version of the NAM. And then we have an experimental WRF NNMB that are currently run. All of these on the NNMB framework within WRF, the Weather Research Forecast Model. So then we have the RAP. This is on the ARW dynamical core with its high resolution counterpart, the HRRR. And from there, we have two experimental models, the WRF ARW and the WRF NSSL. So, for now, the blue is NNMB. The red is ARW. So what's going on now? Well, we have the GFS, and you'll notice that's in green. That's because it's actually using a third dynamical core, and that is the FV3, or Finite Volume Sphere Cubed. This is the future of the UFS. We'll get into that in just a second, but that has the WRF FE3 as its convective allowing model. Now, we've been trying to determine for a while whether it would be the NNMB, the ARW, or the FE3 that would be the future of modeling. The NNMB got kicked out pretty quick for that, and so the WRF NNMB is already no longer running, at least properly anyway. But the NAMs still are, so we still have plenty of NNMB-powered models that are sticking around. And all of these high-resolution models, from the NAM 3 kilometer to the HRRR to the experimental WRFs, including the ARWs and the FE3s, all come together to produce the HREF. And this is where the complexity peaks, because we have a variety of deterministic models put together to be an ensemble. But this isn't a true ensemble. It is a pseudo-ensemble at best, because these models are not built to be a part of an ensemble. They've been stitched together to do so, and as a result, we have limitations as to whether this actually captures the realistic range of possibilities, because they don't explicitly account for error in observations. So let's talk about this new framework and how it's going to make some improvements to what we currently have. The biggest thing is that it's going to be comprehensive. We're talking about the atmospheric modeling component within this video because that's who I'm talking to. That's the audience that cares. But there are a variety of other things going on. With ocean modeling, the full Earth system is going to be modeled using the UFS. Then we have that it's community-based. This is going to be open source. The WRF was open source. This will be open source as well. Everything's available on GitHub, and that means that experimentation and research can continue. And finally, it's smart. It reduces compute resources, it streamlines the framework considerably, and that makes it all the better from the standpoint of NOAA, especially as funding comes under scrutiny. So let's talk about the FV3 dynamic core. I said it was the future of the UFS, and it is. It's the computational engine. So it's going to be the heart of the UFS, and it provides a few things that made it win out in the battle of the cores, if you will. The first is that it has superior computational efficiency, especially when it comes to massively parallel supercomputers, or in other words, numerous supercomputers stitching themselves together to run a model. It's just simply faster than the other dynamical cores. It also has scale-aware physics. That means that it knows whether it's running at a scale of 1 kilometer, 3 kilometers, 12 kilometers, and can adjust accordingly. And it is the basis of both the GFS and the RRFS as a result of these things, so we're going to have to get used to both the strengths and the weaknesses that the FV3 dynamical core has. So let's elaborate. This will be brief on the Earth system coupling. There's some integrated domains that are going on, so everything is working together within this. All of the observations and the community physics package, all of that is coming together. And so we're no longer in an atmosphere-only domain. We have the atmosphere, but we have a few other things as well. We have the ocean, we have sea ice, we have waves, we have land as well. And so we have a large variety of now different factors that are being modeled together. This is going to improve things like hurricane modeling. This is going to improve things like winter weather forecasting, storm surge forecasting, and even things like topographical features within the Mountain West or in the Ozark Plateau. So that's all huge, that's all pretty important, and these are all massive improvements that are coming along here that are exciting, but don't necessarily impact, especially in the short range, the forecasting all that much. So here are the core applications of the UFS. We have medium range weather, that's going to be using the GFS. Short range weather, that's going to be using the RRFS. Subseasonal forecasting, or season to season, that's going to be using the MOM6 model primarily, and the CFS. And then we have hurricanes, the HAFS model. That's for another time, that's for another video, perhaps made by someone else, but essentially the HAFS will be replacing the HWRF and the HMON hurricane forecasting models. So let's talk about the RRFS transition. This is the future of short-range guidance. The RRFS is going to be the successor to the HUR and the RAP with convective scale ensemble data assimilation there to help with radar, satellite assimilation, things like that. 3-kilometer grid resolution that matches the HRRR. Simplifies the regional suite. The legacy NAM is being retired entirely. And, in theory, improved severe weather probabilities for tornadoes, hail, and wind will be forecastable. There are some limitations there, and we'll talk about that in just a second. But with this new system, the rollout of the GFS version 17 will be coming out. This will be a transition from the current physics scheme to the Thompson physics scheme within the GFS. There's been some improvement in skill. And then in an ideal world, it's a pretty simple pipeline. We have the REFS, that is the Rapid Refresh Ensemble forecast system, and its control member is the RRFS. Now, we were just talking about how the HREF is not explicitly made to consider all convective possibilities. The REFS is. It has 6 dedicated members within it that have slight disturbances to initial conditions and physics in order to create a realistic range of scenarios. It's an ensemble that was tailor-made to be that way from the beginning, rather than stitching together a bunch of deterministic models. That's an improvement. Then we have the RRFS, all of this based on the FV3 dynamical core. But there's one small problem I haven't mentioned yet. It's not the best dynamical core in terms of accuracy. It's more computationally efficient, but it is not the most accurate. That goes to the ARW, which is why the RAP and the HUR will still be sticking around, and you'll be seeing the HRRR as a part of the REFS as a 7th member. This is pretty important because it does signify that there are still some problems that need to be hashed out. So let's talk about the challenges of the FV3 dynamical core. The first is its convective scale hurdles. While it's good at global scales, the FV3 dynamical core has served the GFS pretty well so far. It has had some criticism at smaller scales, again, especially compared to the ARW dynamical core. There are higher levels of omega noise and complex terrain. It overcomputes omega as well, sometimes by a factor of 2 or 3 compared to its other models. It has issues with grid scale artifacts, especially in high resolution reflectivity simulations, where you will have very high storms, you will have very high reflectivity values that are not representative of the real world and are not shown in other dynamical cores. And it also has some mass conservation and stability issues, especially in convective environments. Again, it looks like there are some issues with convective scale omega in particular that might make it difficult to resolve. So these are some of the challenges, at least on the more technical end, of the FV3 at convective scales. Again, at global scales, it seems to be doing pretty well, but at those convective scales, that's definitely a struggle. The other thing is the controversy for selection. The adoption of the FV3 over community favorites is definitely a point of contention. Now, GFDL's institutional influence at NOAA seems to have outweighed some objective performance metrics, including their very sensible claim that the computing performance is worth it. There are a lot of reasons that the FV3 ended up being good, developed by GFDL, and it looks like they definitely had a reason, a say, in the reason that this went. And obviously, being the party that developed a dynamical core, you'd want to see it in use. So that is not surprising. It also has a perceived step back. That's another part of the controversy, in short-range guidance in particular. And some in the forecasting community have really noticed that. And then finally, there's a steep learning curve for researchers transitioning from the WRF to the UFS framework, despite the fact that the WRF is still largely in use. Now, one of the good news things about the UFS is that there is open source collaboration. It's GitHub driven, so all the code is there. There's support from EPIC, that's the Earth Prediction Innovation Center, and that's awesome as well. And given that, we have unified science between researchers and operational forecasters, and there's cloud portability. That's why these problems are able to be diagnosed in the FV3. There's supposed to be some published literature later this year, and there already has been some. And that's because it's all open to everyone, and that's awesome. I think that open source collaboration is one of the most important things we can do in science, and that's a place that the United States has been leading away for the long time. So let's talk about the RRFS transition once again. One of the biggest goals was to reduce complexity, and you'll notice that this flowchart is significantly less complicated than its predecessor, but it's leaving something out. Because the FV3 has some of these problems, there's another parallel chain that's running with it. It's using up more compute, and that is increasing complexity. And this is getting in the way of that reduction of complexity mission, but it is also giving us a much more promising place to go. And as a result, by around 2030, I'm expecting we're probably going to start to see a transition yet again, an upgrade to the unified forecast system from the WRF and the FV3 to the MPAS. There's a GFS MPAS that is currently in the works at NOAA, and it might have a resolution as high as 3 kilometers going out to that 384-hour lead time. We'll just have to see, but it was made very clear earlier this year that the National Weather Service intends to make a global 3-kilometer model based on MPAS. There are a variety of offshoots from this. The GSL MPAS RRFS looks to be the version 2 of the RRFS that will be replacing the FV3 version at some point in the near future after the FV3 version becomes operational. There are then the NSSL variants of MPAS, the HTPO and the RN, that are going to serve as very similar counterparts to the current WRF experimental models. One goes out 48 hours using HRRR current conditions, and one goes out the full 84. It's the MPAS RN. As of now, these are currently available to use. The GSL MPAS RRFS looks to be very promising, nearly as skillful as the HRRR, despite how young it is. The NSSL MPAS HTPO is explicitly for convective situations. It's very good with morning convection and stratiform rain. And the NSSL MPAS RN seems to be the overall best for severe convective storm forecasting in general. But these models do unfortunately lag behind in terms of when their runs come in, meaning that the lead time is a bit larger than it is on other models. So with that being said, thank you so much for watching this video. I hope it was informative on the UFS, both the exciting parts of it and some of the limitations. I hope to see you in the next videos, wherever my journey takes me, and I hope that you will stick around on Claws for when additional forecasts come out in the fall semester by the new broadcast meteorology students. We'll see you then.